All right, so let's talk about yellow lights. There's a lot of ways to do a yellow light for this lab, and you can do this as a state machine, but it's a really kind of complex state machine. And when we talk about Verilog, we'll have the machinery to do this as a full-blown state machine without too much trouble. But you don't want to take that approach because you get really big tables and complex circuits. It's pretty unlikely that you can actually build it. So there's a trick we can use. So in your previous traffic light version, you were generating a red light or a green light. Okay, so let's think of this as a go signal. Okay, so here's your previous circuit, and it's got inputs from sensors. And let's just look at one lane. Okay, it's going to be exactly the same circuit for every lane. So let's just look at, for example, west control. It's going to be the same for south, it's going to be the same for east. So your previous circuit generated a signal, okay, which used to say green, and it used to generate one for red. Okay, we're going to ignore the red. And we're going to rethink what the green light says. Green light basically says if you're on this lane, you can go. Okay, so we're going to change this from green to go. And go means you have priority. So that's the exact same circuit from your previous lab. Rip out the red light and just take the light that used to drive the green and think of that as a go signal. Okay, and we're going to build some additional circuitry that's going to generate three lights: red, yellow, and green. So this is new circuit. So keep your old circuit. And you're going to have three of these. Okay, you're going to have your previous circuit that generated a go signal for west. That's going to go into a new circuit, generate red, yellow, green for west. You're also going to have part of your previous circuit that generated a green signal for south, right? Call that go for south, put it into another one of these new circuits that'll generate red, yellow, green for south. And then a third time for east. All right, so let's look at this new circuit. All right, the main thing that you need here is you need your go signal to go into your delay. And this is your delayed go, so D-go. And let's look at some timing diagrams. So suppose your go signal is low, and then it eventually goes high, and then it eventually goes low again. And your delayed go copies this, but it has a delay. All right, your go signal is low, means you don't have permission to go. Your delayed go signal is also low, means that this is basically what your go signal was 2 seconds earlier, right? It's a delayed version of go. So if your current signal says you don't have permission to go, and if 2 seconds ago you also did not have permission to go, what color should your light be?
Red.
Should be red, right? Absolutely. You don't have permission to go now. 2 seconds earlier you still didn't have permission to go. This should be red. All right, let's take a look at a point in here You have permission to go from your circuit. Based on the sensors, you've got the highest priority. But 2 seconds earlier, you did not have permission. So you just got permission somewhere in the last second or so. What color should your light be?
Yellow. Red.
Should be red, because we don't go through yellow to go to green. So that's still red. Right? And we're waiting a few seconds before we go green. All right, so let's look out here. Now you have permission to go, and you had permission 2 seconds ago. Now what color is your light?
Yellow.
Green.
Green, right? So you got permission, you had permission. That's green, not greed. All right, final possibility. You no longer have permission. Somebody else showed up with higher priority, but 2 seconds ago you did have permission. So now what color is your light? Now it's yellow. Okay. Right? Because this basically means we just lost priority. But we're not going to turn red right away. We're going to turn yellow first. But after 2 seconds, our delayed go will be low again. That's when we're going to go red.
Wait, so we turn yellow on after red? I'm sorry, after green.
After green, if you're losing permission, we go to yellow for a few seconds, then we go to red.
Okay.
Right? If we're red, we go straight to green after a few seconds. All right, so this is the part you want to make peace with. Okay? Building a circuit to do this is going to be really, really straightforward. But make sure you understand this and you agree with it. Right? So talk this over, ask questions, argue with your lab partners, draw some pictures, play with some cars. Convince yourself this is the right thing to do, okay? And once you believe this, now we can make a circuit for it, and it's really, really easy. So that's an ongoing process, but let me show you what we do with this. We make a truth table. Here's go, here's delayed go. Here's red, green, yellow. And we got 4 possibilities. All right, if go is 0 and delayed go is 0, we said we want our light to be red, right? So red's going to be a 1, green and yellow will be 0. So these, right, 1 equals on, 0 equals off. All right, if go is 0 and delayed go is 1, what color light do we want lit up? Go is 0, delayed go is 1.
Yellow.
We want yellow, it's the state right here. So yellow will be 1. These will be 0. If go is 1 and delayed go is 0,
Red.
that's red. And if go is 1 and delayed go is 1, that's green. Now you got a truth table. This is a 120 exercise now. Write equations for red, green, and yellow in terms of go and delayed go. Simplify them, build a circuit, you're done. All right, and this is going to be really easy. This just looks like the inverse of delayed go, right? 0 becomes a 1, 1 becomes a 0. This one's even easier. This is just an AND gate, go ANDed with delay go. And this one's a little quirky. It's delayed go ANDed with not go. So you need an inverter there. But a couple of gates, and you've got circuitry to generate red, green, and yellow. For your west lane, because you're feeding in the old green signal from the west lane. Make another delay circuit, make another set of logic to implement this truth table, and that's your south lights. Make another delay circuit, another copy of this, that's your east lights. Put it together in a wiring diagram, pin numbers, part numbers, double check it, triple check it with each other, and then go ahead and build it. Right? And you can build one lane at a time and make sure that it works, right? And what should happen is you set the switches so that car has permission to go. It should take a few seconds to turn green. Set the switches so another car has priority, and it should go yellow and then red.
So to clarify, we have to create 3 new circuits, the new circuits for each direction.
So each direction is going to have a delay circuit, and then 3 of these circuits for implementing the lights.
All right.
So you're going to have a total of 3 delay circuits and probably 9 logic circuits, although one of them is just going to be an AND gate, or 3 of them will be an AND gate, and so on. All right, can you do that? And it's pretty cool once it's working. And if you finish it early, I have a test bed which I will bring in Thursday to show you. It's sitting in my office right now. But it's a little model of a 3-way intersection. And there's a traffic light hanging in the middle with red, green, and yellow LEDs on 3 sides. And there's some cars. There's a Mustang and I think a Lamborghini and something else. And they have magnets on the bottom and there's sensors underneath the road. And you can pull the car up and it will send the sensor to a switch. And you can take your circuit and hook it into this test bed and then actually like play with cars and see the lights change. Yeah?
Are we going to have it set up so then east and west can both go at the same time?
No.
No.
No, keep it simple.
I mean,
Simpler.
like later on in this.
No, this is as far as it goes. There'll be a good new experiment. But don't tell anyone or they'll copy it. All right, good enough? Okay. That's a lot of circuitry and a lot of wiring. But a fairly straightforward design. All right, let's do state machines. We got 40 minutes. I would like you to, how many people we got? Let's find like groups of 3 people maybe, and get about 5 groups. And find a spot on the board. Make sure you have a good marker. If you don't, let me know. There's erasers scattered around, including a rag up here, so you can erase. All right, so let's work on question 6 in groups. And so first question, what are the inputs to this circuit? There's really only one input, which is X. Okay, so the clock is never considered an input. Okay, it should never show up in your truth table. We understand there's a clock and it's sitting there and it's running in the background, but we don't actually list that in the state table. And Z is an output. It's coming from the output of an inverter. Y1 and Y2 are coming from these Q outputs. The only input is X. Okay, so we have one input. We have 2 flip-flops. How many possible states do we have? How many combinations of 2 bits are there? 4. Okay, so your state is really the combination of your flip-flop values. So they could be 0, 0, 0, 1, 1, 0, or 1, 1. So there's 4 possible states, and there's one input. Okay, so you're going to make a really wide table, and you want to start off with your input value and the flip-flop values, so Y2, Y1. And you're going to start something that looks like a truth table by showing all the possible values of those. Yeah.
It's also quick if I write down Q1 and Q2 instead of
You can use Q2, Q1, or you can use Y2, Y1. Just make sure you stick to one or the other throughout the problem. But they're exactly the same thing, so.
Yeah, but
I prefer the Qs personally, but.
So the 0 is 0, 0. Oh, like that.
And you don't need to list both Q2 and Y2. You can just do either Y2, Y1 or just Q2, Q1, because they're exactly the same as each other. So you can do whichever one you like, but no need to do both. All right, and then let's leave space next to this for a column we're going to go back and fill in a minute, but just leave an empty space here for now. And our goal is to figure out what the new values of Y1 and Y2 or Q1 and Q2 will be after the clock ticks. Okay? And to figure out what the value of a flip-flop is after a clock tick, you need to know what the inputs to that flip-flop are. So these are D flip-flops, so we need to know the values of D1 and D2. So go ahead and make columns for D2 and D1. And how do we figure out the value of, say, D2?
We observe like where the input's coming from.
Yeah, you got to analyze your circuit just as a plain old combinational circuit. So what does D2 come from?
OR gate.
Coming from an OR gate.
Q1 and Y2.
Right, so it's an OR of Y1, Y2 or Q1, Q2. So somewhere nearby, I would start writing some equations like D2 equals Y1 or Y2. And then write down an equation for D1. All right, and once you've got those equations, now you can fill in ones and zeros for D1 and D2 in your truth table. So for example, D2 is the Y, is Y1 ORed with Y2, so OR these two columns, that'll give you the values for D2. And you already did that, good. And then D1 is X ANDed with Y2, okay, good. Yeah, double check D2. Yeah, you got it. Those might be better. No guarantee. All right, so based on the value of D1, we can find the new value of Y1. Based on the value of D2, we can find the new value of Y2. So these are D flip-flops, so it's also useful to make a picture, a truth table of what a D flip-flop does. So D is the input, Y plus is the value after the clock tick, and D flip-flops, the output's just equal to whatever D was when the clock ticked. So using this table, or your knowledge of D flip-flops, you can now make columns for the new value of Y2 and the new value of Y1. And for D's, it's pretty straightforward. It's just the same as D2 and D1. Double check D1 before you do Y1 plus. So D1 is Y2 ANDed with X. Yeah.
These are not supposed to be the same thing. These are supposed to be when we plug, let's say D2 is Y2.
Okay, and then go ahead and make a column for Z also.
Should be 1, right?
It's basically
And D1. D1 down here. Y2 ANDed with X. Oh, okay, you're right. You're right in order. All right, so go ahead and do Z. And so you can write an equation for Z.
Yeah.
Is in the inverse of Z based off the next state of Q, Y1 or?
Z is based on Y1 and Y2. Right, so the current value of Y1 and Y2.
What's the inverse of D2?
Yeah.
Is that before or after context?
Z?
Yeah.
Yeah, Z is based on the current value of Y1, Y2, so the value is on the left of your table. So what? Yeah, it's the inverse of D2. Exactly. All right, so you got Z good.
The output of C is actually.
All right, perfect. So let's add one more column over here to the right of Z. And this first column over here that we left space for, let's label that current state. And then a new column to the right of Z, let's label that next state. And now we want to come up with names for our 4 possible states, right? Our states are Y1, Y2 equals 0, 0, 0, 1, 1, 0, or 1, 1. We're going to come up with some sort of name for those, and an easy name might just be A, B, C, D. But whatever you choose to call it, make a table that show the possible values of Y2 and Y1. And then let's just make a column called name, or state name. And I'm just going to go with A, B, C, D, but you can call it whatever you like. All right, and then you fill in the current state column based on the current values of Y1, Y2 using your table, and then you fill in the next state based on the next values of Y1, Y2, Y1 plus, Y2 plus. with your ordering, because you said if y2 is a 1 and y1 is 0, that's SP. Yeah, you're right. Ignore me. I think you were right.
Is it all weird? So just took up some time to work.
No, I think you had it exactly right before. I think that was wrong.
Should be right and in the right order.
Yeah, okay, good. Okay, good. Okay, so if I do A, B, C, D, right, this was A, B, C, D, A, B, C, D, and the next state was A, C, 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 A, C, D, D. Okay, and that may come out different depending on the order in which you wrote y1, y2, and so on. But this is all the information we need now to make a diagram. Okay, and basically we're interested in the input, so any inputs that you have, and the current state. And given a particular input and current state, this will tell us what the output is and what the next state is. And that's all the information we're going to capture in our diagram. Current state, input, next state, output. All right, so you want to look at your picture and you want to ask yourself, is this a Mealy machine or a Moore machine? So a Mealy machine, the output depends on the inputs as well as the state. A Moore machine, the output only depends on the state, does not depend on the inputs. So if you look at your equation for Z, it depended on y1 and y2, that's your state, does not depend on the value of x. So this is a Moore machine. Okay, so with a Moore machine, we can draw a state diagram like this. We can list a state, and then since the output only depends on the state, we can list the output value inside this circle that corresponds to the state. So we can list Z right here, and then our transitions depend on our current state and our value of x, and we're going to draw an arrow pointing to whatever state we go to for that initial state and that input. And so now you make 4 circles for your 4 states, A, B, C, D, or whatever you called them. Show the output of each state below it, and then draw arrows from one state to another based on what your diagram is telling you. If you're in state A and your input is 0, your next state is A. So you just draw an arrow back to yourself labeled 0. If you're in A and your input is 1, you also go to A. Right? So try to draw a picture from that, and then you're done.
So this one, it could be 0, 0.
Look here. How would I diagram this? The arrows and pointing to different columns.
So if you're in state A and your input is 0, what's your next state?
Actually, it would be Z, wouldn't it?
Z is an output. What's the next state?
A.
A. Okay, so if you're in A and your input is 0, you go to A. So draw an arrow from A to A, label it 0.
Well, do I just deal with X, or do I call it just 0?
So if you have a key, right, like this, that says the label on here is the value of X.
Yeah.
If you had multiple inputs, you could say X1, X2, and then you could just label it with the 2 values of that.
Okay.
Right? It's a shorthand of, instead of saying X equals 0, but that's basically what it means.
And then if I put a Z down here, depending on
And so Z you can put in the same state underneath the state name. So if you're in state A, Z should be a 1. So you just put a line and then put 1 underneath it.
Okay.
Again, it's just following that key.
Okay.
You did the one in the hallway.
Maybe.
Maybe. Okay, that looks good. All right, cool. I think everybody's got it. So what might this look like? So here's A, B, C, D. So the output should only depend on the state. So state A, the output is 1. All the other states, the output is 0. So I'll put a 1 here and zeros down here. And then you just fill in like you did. So if you're in state A and your input's 0, you go to A. So there's a 0. If you're in state A and your input is 1, you also go to A. All right. And you can say x equals 0, x equals 1, but if you have a key which labels this arrow as x, right, then you know that x is a 0 here. If you had multiple inputs, if you had x and y as inputs, you could say x, y. Then if I said 0, 1, you'd understand x was 0, y was 1. And you can start getting into abbreviations like that where you say x equals 0, comma 1, but for starting purposes, I would go ahead and draw 2 arrows just to avoid ambiguity. So state B goes to state C for either a 0 or a 1. So there's a 0, there's a 1. State C goes to C or it goes to D. So if C is a 0, it stays in C. If it's a 1, it goes to D. And state D goes to C or D. So there's a 0. And there's a 1. And I think that's what everybody has. All right, so this is your punchline for the whole problem, right? All of this is really just so we can make that diagram. And all of this and this is really just so we can say for current state and input, what's the next state, what's the output. And then those columns turn into this diagram. And this is a much easier way to look at what your machine does. For example, we can see once you get into state A, you're stuck, right? So if both flip-flops are ever 0, 0, that's it. Machine's going to be stuck in state 0, 0. The output's always going to be a 1. But if you don't start off in that state, nothing else is going to take you to that state, right? So that's a bit of a dysfunctional machine. And nothing will ever take you to state B. But if you happen to start in state B, you'll immediately come down to state C. And mostly we're just going to bounce between C and D. And if you're in state C and you get a 1, you'll come here, and then when you get a 0, you'll come back to C. And that's pretty much all the machine does. Now, is it useful? Is there a reason for that? That's not our concern, right? We're just the designer who implements the machine or analyzes the machine. We didn't come up with it. But that's a complete analysis of that horrible mess we started with. All right, think you got the idea? All right, so let's do another one. And let's go with this one from the book. Did we do this one last time? No, let's not do that one. We did that one last time. Let's do this one. All right, there's a nice vicious circuit.
Okay.
And we may not finish this by 15 minutes from now, but see what kind of progress you can make on it. And the more you do this, the faster it gets.
Is there a way you could zoom out on that?
Yeah, let me pull up a better picture of that. Too zoomed as it gets. And there's a bunch of space in the middle boards back there if either of your groups wants more space.
I'm looking at this, I like to make true table for this. Do I use S1, R1, S2, R2?
Yeah, that would be good.
And then the clocks don't matter, right?
Clocks don't matter. Everything should be connected to a single line, which is just a system bug.
Okay.
And it doesn't actually come into
Yeah, it's
any of the
too big
analysis.
truth table.
Yeah.
Q1 is not Q1. Yeah, it is going to It's going to, reading out of not Q1, going into the not AND gate. That's going to give us J2.
Oh, not Y1. Okay, yep. Okay.
Is this the correctness?
Would you count K1 as
Y1.
Yeah, I guess it's, yeah, okay. Now, so that's probably the next.
Yeah, but those are just inputs to the flip-flop. So you want columns for J1 and K1 in your table.
K1
And based on what a JK flip-flop does, you write down what the second Y1 is plus the
Yeah, that is.
You want a better marker? I can get you a better red one.
talk about the one on the left side?
Yeah.
But isn't that having to put into it's not
No, the X, so basically K1 is going to be the, it's going to be
And then
the,
Y2.
Oh, that's going up though.
yeah, that would make
Yeah.
okay.
Oh, no,
Now
now
So you got X, Y, T, Y1 as your current state. And then your inputs to your flip-flop is not going to be D1 and D2, they're going to be J1, K1, and J2, K2. Okay.
Q1 to Y1.
Y1 is
Never mind, we got one.
So,
Because we need.
are you writing the?
That's the new
So, if it's a J
has
flip
not
flop,
Y2.
what the other?
B inverse
Okay.
So J1.
It's going to be the inverse and
Oh, you can use Y2 for the
Zero. Yeah, whatever it was before. Zero, one is zero, one.
So
So really quick. So not Y1.
So once you know what J1 and K1 are, and you know what Y1 is, you can figure out what Y1 plus is.
So it's not the first two.
So last time, oh, wait, you have to write one. Oh, yeah. You have to write
I wanted to do everything.
it's the Q1 not that comes out.
So it's like X is 0,
So if an X or wait, what?
then you do
That's like, yeah, that's Q1. So that is Q1. So K1 will be X4, and then X is the arrow, Q1 is the arrow.
X 0, 0, and Y is 2. And then this would be 0.
Oh, okay, okay, I think I know.
Yeah, which probably would try to
Okay, so
that would be probably.
Okay, now.
Well, you know what?
That would be at all, right? Y1 bar is equal to right. Oh, no. X or Y or well, not that's true. Well, and 0 is no, you inverse. Zero or Y1.
Now,
X or T0. And then anything. The first one, you put the zero, and then you go now. Yeah.
and then the next one, that's right. So then the next one is gonna be zero.
We don't have to do that, we can do it right here, for all we know, we can do it right here.
You insert this So, on this section, we're only looking at Y1. Yeah. And then on this one.
Yeah.
So, pretty much all it is for.
Start the out, here's the out, so we have to plug in, y, or, y, so,
Y1 with an F.
Yeah, well, that's
we have to do, what that state for y1 and y2. Alright, so now I got it.
Or
It's a NAND.
It's only a output. It's just strictly one.
Y1
Yeah, that's
and then it's and with X or Q1 only one at a time.
I think this is one.
This can be simple.
This
one,
And then the,
All right, so I'm seeing good equations for J1, J2, K1, K2, right? And then probably the hardest part of this is filling in those entries, because you got 4 columns to fill in, you got 8 rows, so you got to do 32 XORs and ANDs and things like that. And that's a lot of legwork. But I would say do the first few rows of these, and then let's because we've only got about 5 minutes, do the first few rows of these, and then move on, and let's talk about finding Y1 plus and Y2 plus. Unless you already did all 8. So the flip-flop behavior looks like this for a JK flip-flop. You have 2 inputs. So we got 4 rows in the sort of truth table for a JK. And if J and K are both 0, what does a JK flip-flop do? What's its output going to be equal to? it stays the same. So the new value of y is going to be the same as the old value of y. If k is a 1, it doesn't care what the current value is, it just forces it to a 0. If j is a 1 and k is 0, it just forces it to a 1. And then what if j and k are both 1?
It becomes the inverse of whatever.
Right, it becomes the inverse of what it was.
Yeah.
So there's your excitation table for a flip-flop, right? If you know what the inputs are, here's what the new output will be. And so you go through your state table that you're making, and if you see that J2 is equal to 1 and K2 is equal to 1, you look at the current value of Y2, and the new value of Y2 will be the opposite of that. And so you're still filling in Y2 plus and Y1 plus, but here you got to take into account the J input, the K input, and maybe the current value of Y. Right, so there's more things to look at, but it's exactly the same process. It's just more work potentially.
So,
S2 is coming from Y1 bar, it looks like. Yeah, that line right there goes into there and comes down. Because if it's an input, it's not driving it, so you got to find one output somewhere along that line. And it's easier maybe with a highlighter or a color pen or something to trace it, see everywhere it goes, and then figure out which one's the output.
Oh, yeah, all one. A1. I mean, well, we have to do anything.
Zero.
Like now, we can be worried about like, this is always first. Yeah.
Well,
Z would just be.
yeah, it would just be,
Z would have to be. Would be K1. Inverse of K1. It would just be K1. Plus Y1. And 0, 1, and then and that. Or what? Yeah.
That'll be a 0. And then that would be banded with inverse.
All right, so I'm starting to see some values for Y1 plus and Y2 plus, and those are looking good. Those look really good. So the last thing you're going to need to do is fill in the output, right? And your output is just another equation. It depends on Y2 and it depends on Y1. So this is another Moore machine, right? The output only depends on the state. If the output depends on an input, then it's a Mealy machine, and so you list the outputs on the arrows, right, based on the state. But this is going to be another Moore machine. All right, so we're just about out of time here. So I have office hours tomorrow morning at 8, tomorrow morning at 9, Thursday morning at 9, Thursday morning at 11. Okay, that's 4 hours. And you have to compete with people coming in for advising, but that's tapering off right now. So please, 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 right, if you're having trouble with this, come into office hours at least one of those times, and let's work through these. I think everybody's got the process down, right? It's just you try to do it, and you'll forget what you're supposed to do next, and so on. Just keep working on it. Let me know if you have questions. Come and find me. Shoot me an email, whatever, okay? And see if you can get these done by Thursday.
I have a quick question. So, like, what is the truth table for an SNR gate?
Oh, so for an SR latch, let me mention this one. So for an SR flip-flop, if SNR is 0, it doesn't change state. 0, 1, it sets it to a 0. 1, 0, it sets it to a 1. So that looks exactly like a JK. If 1 and 1, let's go ahead and say that's going to output a 0.
Oh.
So that's called a reset dominant configuration, and that's the one that the book uses, so I assume that's what they want to use in the exercises. So there's your forbidden state suddenly allowed. All right, work on those. Let me know how it goes. I'll see you on Thursday. And Thursday we'll start doing synthesis.